Hello again. Okay, welcome to this second video in my new series about genetic algorithms and evolutionary computing in general. So in this particular video, I am going to talk through the actual algorithm itself. Now, if you can't remember what I'm using as my demonstration to demonstrate this idea of a genetic algorithm, I'm looking at the problem of finding the phrase to be or not to be, that is the question, in a sea of random to be or not to random phrases. So to demonstrate this idea, I have this particular P5 sketch running in the browser, and it's just generating random phrases over and over again randomly. Now, at some point after some gajillion amount of years, we might, it could happen right now. This could be the moment where we could be so unbelievably lucky and we would just all go buy our Powerball tickets, where to be or not to be actually appears right here, but I'm pretty sure that it's not going to. So this is the brute force problem. The solution to this brute force problem, I'm going to refresh this here, is to use a genetic algorithm. And you can see that this is now the example that I'm going to get to of the genetic algorithm running, and you can see it took a matter of 5 to 10 seconds to find this phrase to be or not to be, and that is the question. It took a number of generations. There's this concept of fitness. There's this idea of a population. There's this thing called a mutation rate. So this is what I need to cover. What are all the pieces of the genetic algorithm? How do they work? What is the order in which they happen? And then after I do that, we'll start looking at how all those things are implemented in actual code. And I'll look at both JavaScript code that you can run in the browser, as well as Java code that you can run in the processing programming environment. Okay. So coming back to the algorithm, let's check out our car, by the way. So this, by the way, I'm just letting this run in the background. You can see that these cars from Boxcar 2D are really evolving quite nicely. I want to credit whoever made Boxcar 2D because I really love this project. So I don't know it off the top of my head, so I'll mention it in a future video and I'll make sure that it's in the description of this video. But you're going to have to go to the website itself and find it. Okay, so we'll check back in on our cars in a little bit, our cars. But right now I want to go back to this kind of presentation. So now, I don't usually use slide presentations in my videos, so feel free to complain in the comments if you want to. But before I even get to the algorithm itself, I want to talk about, now, I want to mention something. As with most of my videos that are part of the Nature of Code series, I'm doing a thing where I'm kind of saying, this nature stuff, this physics stuff, this biology stuff, it's really interesting. And I want to be inspired by it and try to kind of approximate it in software to create compelling and interesting and unique creative projects. But I'm not actually here saying to you, I'm a kind of like formal, rigorous scientist who's trying to do a formal experiment about evolution and model evolutionary processes precisely in software to study some type of actual biological process. The idea of a genetic algorithm is simply like this idea of inspired by actual events, right? Based on a true story. This genetic algorithm takes ideas from actual biological evolution and applies them in software. But I just wanted to sort of a disclaimer to say that I'm always kind of scratching the surface of the actual topics of genetics and evolution. But if you read Darwin and think about Darwinian natural selection, there are 3 key principles that need to be in place for evolution to happen. And those principles I want to make sure are in the genetic algorithm that I demonstrate to you. So first I want to just talk to you what those principles are. The first one is heredity. So if we're going to have this idea of elements of a population that evolve from generation to generation, there must be some mechanism in the algorithm in our code that allows data from one generation to be passed from one to the other. So that's one thing that's going to have to be there. Variation, right? Let's say I want to evolve whiteboard markers. And this is my population of whiteboard markers. I only have blue ones. And these whiteboard markers are going to somehow make children whiteboard markers. This is getting a little bit weird. But the point is there's no variation here. These are both blue. So they could make a child and pass down their traits, their data to the next generation, and they would be blue. And then there'd be more blue, and there'd be more blue. And I want to have some pink ones and some purple ones, some orange ones, and all the colors of the rainbow. I'm off track here, but you get the point. There's got to be some variation. And what's the mechanism in order for there to be a variety of traits either in the population when it starts or as the population evolves over time? So that's another key principle, variation. The last principle, which must be present in the genetic algorithm, is selection. Selection. There has to be some way of saying, here's I can't believe that I'm using whiteboard markers. I should have thought about this in advance. And brought some like stuffed animals would have been great. Could have brought some stuff. That would have also been weird. Stuffed animals? Weird, yeah, okay. But anyway, this is my population of whiteboard markers, right? If I just say every single one of these whiteboard markers has an equal chance of passing its genetic information down to the next generation, next generations, next generation, oh my God. Then there really won't be evolution at play because nothing will, the makeup of the population, the quality of the population will not really change over time. However, if I were to say something like brighter colors are more likely to have their genetic information passed to the next generation, then I might be more likely to pick red or more likely to pick this green. I don't really have any bright colors, darker colors, whatever. The point is that there must be some process of selection. I should just read this to you. Mechanism by which members of the population have the opportunity to be parents and pass. So this is, by the way, typically referred to as survival of the fittest, right? This idea of fitness. And this idea of fitness will play a big role in the genetic algorithm. And fitness will actually become a mathematical function, which is somewhat absurd and not how things don't work in the real world. We're all walking around with a hat on, and then there's a number on our hat that says our fitness as a numeric quantity, and the higher our fitness is, the more likely we are to pass our genetic information, right? But this is this idea of this kind of almost cold, algorithmic version of this kind of beautiful and amazing natural process. I'm using sort of mathematical function to calculate fitness. Okay, so this is the idea. I must make sure these three principles are present in the genetic algorithm. So I'm going to whoop, that's our car. We're checking on our car again. It's not one car, by the way. It's been, actually, maybe it is. I wonder if it pauses, actually, when I take the window out of focus. But whatever it is, it's certainly evolving to do cool and amazing things. I want to go back to this. So I want to talk through how this algorithm works. And I'm going to use natural selection to pick this purple marker. And then I have to press a button, that button, to come over here. And let's talk about, now, what I want to do, I really want to use unicorn, but unicorn has too many letters in it also. Maybe I'm going to use unicorn. Gosh darn it, I always just use cat. Let's just say we want a simpler phrase to evolve. I could use rainbow, by the way, but I'm going to use unicorn. I want to evolve the phrase unicorn out of every single, it's not really a phrase, the word, the sequence of characters unicorn, out of every single possible random sequence of characters. So the very first thing that I must do in a genetic algorithm, in the sort of traditional computer science genetic algorithm, I don't know, I just said computer science. I have to put like a quarter in my computer science jar. I love computer science. This is just not a computer science YouTube channel. It's something else. I don't know what it is. Okay, step one is create a population. I'm going to write just pop for short. Can you read this? Create a population of n elements. And let's remember also, down here, what are those three principles I must have? Heredity, I must have variation, and I must have selection. Now, I'm disappointed with myself. I wish I had written variation first in this order, because ultimately this is where we get, in this step, we get our first principle variation. Now, the way I wrote this, create a population of n elements, I don't necessarily have variation there yet. I really should say create a, random, and I think this might be cut off at the top, but I just wrote the word random there. Create a random population of n elements. And really, I didn't write that very well. I should say create a population of n elements with random genetic material. Now, what is this genetic material? This idea of like sort of virtual DNA, digital DNA. We're gonna have to look at how that's encoded in code and stuff later. But you can think about it again. Let's think about it in the context of trying to evolve this phrase unicorn. The population might be a whole lot of 7-character words with random characters, like jorm, pancake. That's the right number of characters. This is really much harder than I thought it would be. I think that might have two. Anyway, so you get the point, right? This could be our population. Unijorm, pancake, and Boy, I'm doing. So this is a population that has variation. Now, does this have enough variation? But this idea that we're going to somehow mix and match these over generations, could I actually get, I have uni here, I have a C here, but I have nothing with an O in this spot, nothing with an R. Oh, maybe I do have an R, nothing with an N in that last spot. So the variation, there's more to variation than just that initial population, which I'll get to, but that's sort of a key principle. Okay, so that's step number one. Great. And actually, you can think of this in the sort of P5GS and processing world of we have a sort of initialization and then a forever loop. This step one is actually the setup function. This is what will happen in the setup function. Okay, step two, which I'm going to draw a line here because this is what's going to happen in the draw function, meaning step two is going to happen over and over and over again. For generation, 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 evolving, evolving, evolving. Step 2a is calculate fitness for, n elements. So we want to calculate the fitness of every single member of the population. This, by the way, is playing a role now of this idea of selection. Fitness is going to be a means, a mathematical function to determine which members of the population are more likely to be selected to pass their genetic material down to the next generation. So that's this idea of calculating a fitness. So there's going to be some sort of loop that will go through all the elements of the population, call a function that will calculate the fitness and give you some number back. So let's think about what could be, so one of the key factors in a genetic algorithm is the fitness function. So what could be, think about it, what could be a fitness function here for this particular problem? Well, I have these three, my population has 3 elements. Instead of n, it's 3, right? And I could calculate the fitness for these. I could say the fitness function for each element of the population is the number of characters that match the target phrase. 1, 2, 3, 4, 5. So this has a fitness of 5. 1. This is a fitness of 1. Oh boy, this one did terrible. This has a fitness of 0. Okay, I might need some different example in a second. I got one for you. Popcorn. And this one has a fitness of 4. This is actually going to work out beautifully for me. So unijorm, pancake, and popcorn. Hopefully I did that right. So you can see that these all have a fitness score. Now, ultimately, there are many things that one needs to do to refine fitness and make a genetic algorithm perform more efficiently and faster or less fast or whatever, but this is kind of a simplistic version of a fitness function. Okay, great. Now, what we now need to do is this. So that's step A. The next step, I'm really just going to call kind of reproduction or selection. I think actually this sort of whole thing is that. So this step B has now 2 parts to it. 2a, b, lowercase a, b1, I don't know, whatever. I have a terrible numbering system here. But the first thing that we need to do, this also needs to happen n times. So what needs to happen n times? And that says reproduction section. That should say, I'm just going to use my hand here, selection. The ultimate goal of this genetic algorithm is to end up with another population of n elements, right? This idea is we start with this random population, we calculate their fitness. This next step of reproduction at the end, we should have a new population of n elements and then go back to calculating their fitness again and doing this over and over and over again. Their fitness scores over time should be getting higher and higher and higher as a whole, as a population whole. So this reproduction selection step is a multi-step process. The first thing that I need to do is pick 2, and for lack of a better word, I'm going to call them parents. And 2 is somewhat arbitrary. So there's a lot of parts of this genetic algorithm that you can kind of play around with. Certainly, you could say that the way that reproduction works in your genetic algorithm is a single element just makes an entire copy of itself. Another way of saying that is that 2 elements come together and mix that genetic information and make a new member of the population. You could say that 3 elements come together. This is all just sort of made up as an algorithm, and you might have kind of creative takes on this. But the sort of classic genetic algorithm kind of follows this idea of 2 parents. So how are those 2 parents picked? Well, this is an interesting thing. And by the way, we're really talking about selection here. We're now in the third principle here. The way that those two parents are picked, there's a bunch of different ways, by the way. First of all, you could just say, you know what, I'm just only going to ever pick the top two scoring parents. So I'm going to pick Unijorm and Popcorn. And I'm going to make all the children from Unijorm and Popcorn, and we're going to have a lot of Popjorms. I love Popjorm. It's my favorite snack. Popjorm, Popjorm. I'm going to mix those two up and make a lot of Unijorm Popcorn children. But really, Pancake, even though it only got a score of 1, we wanted a different way of doing this, a kind of better, the sort of more traditional way of doing this with a genetic algorithm, is not just to pick the top 2, but to actually pick from the entire population, but assign the probability of an element being picked to its fitness score. So the reason why these numbers worked out so nicely is I could write them a different way. I could say 50%, 40%, 10%, 0%. So you could think of this as possibilities. What I'm going to do is I'm going to pick out of a hat. And out of that hat, I have a 50% chance of picking Unijorm. It's going to be picked 5 times as much as Pancake. Popcorn is going to be picked 4 times as much as Pancake. So I could use those fitness scores to assign them to probability. Another way of thinking about this, I've kind of run out of space on this whiteboard, but I'm going to use this spot right down here, is I could think of a kind of wheel of fortune spinning wheel. So Unijorm gets 50% of the pie. Popcorn gets 40% of the pie. This is Popcorn, this is Unijorm, and this is Pancake. So the strangest breakfast ever. And you could think of this sort of spinning wheel here. So I'm going to spin the wheel, and most of the time it's going to land on Unijorm. Often it'll also land on Popcorn, but every once in a while it'll land on Pancake. And that's how I'm going to pick those two parents. So the higher the fitness, the more likely that element is to be selected. So that's step 1. Once I have those two parents, I'm going to make a new, and I'm using the word element just to be a sort of word for a member of the population, a creature, element, thing, but I'm going to make a new element. And making the new element is a 2-step process. One step is called crossover, and another step is called mutation. And this is, by the way, where we get our last key principle from Darwinian evolution. So we had variation because we create an initial population of random elements. We have selection in that we calculate the fitness of each element, and we use the fitness as a probability. It's sort of selection probability. It's probability of being selected as a parent. And now, to make that new element, we have to have some mechanism by which the genetic information of one element gets passed on to the next generation. So I'm going to come back up here. This is my weird paper towel whiteboard eraser. Slightly wet with water, because that seems to work well. And I'm going to describe to you the technique of crossover. So let's say we have Unijorm, and we have Popcorn, right? I don't know why I drew this line here, right? These are two members of the population. The mechanism of crossover says take half of the genetic information, and the genetic information is really just this sequence of characters. Take half of the genetic information from one, like Uni, and then take half from the other. There's 7, so I'm splitting up 3 and 4. Take half of the other, like Corn. Combine those two, and look, we get Unicorn. Now, of course, that's not going to happen magically instantly with the first two things you pick. This is artificially designed to give me the right answer, but this is the idea here, that to make the new members of the population, you take 2 that got a high fitness, you combine those, taking 2 with a high fitness to make a new one, you have a good chance of getting a child with an even higher fitness score for that next generation. So this is the idea. Now, there's a lot of different ways that you can do crossover. You can actually just pick a random midpoint. So sometimes you just take 1 from the other and 6 from one, or 5 from one and 3 from the other. You could do something where you like alternate. Take U, then O, then I, then C, right? Or you could flip it. You could have a 50% probability for each one. You could turn this into binary information and mix up the zeros and the ones and then convert those back into characters. There's all sorts of ways that you can do crossover, but you'll see what I'm doing in my example, which is kind of a conventional way of doing it, is picking a midpoint, taking half from one and half from the other. And as you'll see, these characters are stored in an array. That's what I'm going to get to as soon as we look at the code. So that's crossover. Now, we could say that I'm done. This is it. This is a genetic algorithm. Make the random population. Calculate all the fitness. Create a new generation with crossover. Calculate the fitness again. Create a new generation with crossover. Calculate the fitness again. Create a new generation with crossover. Over and over and over again. That could be it. However, there's a problem. In the case of not having enough variation in the initial population, which is quite a reasonable thing to have, it is often useful to artificially introduce additional variation into this process. So two elements of the population are combined with crossover, but before that child is finished, a mutation is applied. And mutation is typically referred to as a sort of percentage rate. So I might say there's a 1% mutation rate. That means for each one of these characters that was selected, that was combined with crossover, there's a 1% chance that I'm actually going to mutate these characters. What does mutating mean? It could be that I just pick a new character. It means that I could go up or down in the alphabet. In this case, none of that would really matter. My mutation is just going to say there's a 1% chance that a random character is selected instead of the character that comes from crossover. And this keeps variation in the system. This mutation rate, as I'll show you in a little bit when I run the example again, really affects how the algorithm behaves. Is there a lot of randomness, less randomness, that sort of thing. So this really completes the genetic algorithm. This is the full, we have heredity as part of crossover. That's the mechanism for heredity. We have variation in the way that we create the initial population and the way that we use mutation as that last step of making the next generation. And selection as this way of calculating using a mathematical function to assign a fitness score to each element of the population, as well as then using that fitness score as a probability for how that element of the population, whether or not it'll be picked as a parent to pass this genetic material down to the next generation. So in the next video, I'm going to say a few more things, and then I'm going to save looking at the code for the next video. So I'm moving a fan here and this over here. So I'm going to come back over here. Ooh, my computer went to sleep. Come back. There it is. So I want to run this example. Actually, let's check on the car again. And let's think about this for a second. What are some of the steps of the population here? So you can see one thing that's a little bit different is it's kind of doing them all one at a time. So we're seeing one member of the population, but we can sort of think of certain pieces here, like what is the fitness function in this particular simulation? I would assume the fitness function, which you can see here is represented as score. None of these have really gotten a score yet. Come on, let's get, you can see it got a score. It's probably how far did it travel in a certain period of time. So that I would assume, and you can see as the score for these. So that's one thing. Then, you could see, like, as you look at any example of a genetic algorithm as it applies to evolution, you can find the pieces of the algorithm. So let me just look here and see how did we do here. This is a representation of the algorithm. You can freeze frame this if you want. It's also on the Nature of Code website. But you can see this is basically everything I described to you. Step 1 is initialize, create a random population of n elements, each with a random DNA. Step 2 is selection, evaluate the fitness of each element of the population. Then step 3 is reproduction. Pick 2 parents, apply crossover, apply mutation, add the child to the new population, and then step 4 is replace the old population with the new population and return to step 2. So set up this, everything happens initialize, draw happens over and over again. And this is what I'm going to look at in the code in the next example. Great. So actually, I'm gonna end this video now. And in the next video, what I'm going to do is look at how the code works, play with some of the parameters, and see how the genetic algorithm behaves. OK, thanks for watching.